let's go ahead and graph this transformation of a tangent. The first thing I'd like to do is factor the angle. We have a leading minus in here which can lead to some trouble. So let's use the fact that the tangent is an odd function. So what I mean by that, if we look at the graph of tangent, it's symmetric about the origin, which means that those 2 points are on the graph. In other words, if you go to the right and up or to the left and down, you're on the graph. So that's how odd functions work. And with odd functions, the leading minus can be brought to the front like this. And so that gets rid of the minus that's on the inside, but it does introduce a minus that's on the outside. And so now we can apply what we know about these 5 properties. We can look at the leading minus and say, yes, there is a reflection. Amplitude, for a tangent, we say the amplitude is not applicable. The tangent function goes up forever and down forever. And the definition of amplitude is the maximum distance the graph goes from the center line. Well, the maximum distance is not defined here because it goes up and down forever. The period of the tangent is the period of a basic tangent divided by this leading coefficient. So we have pi divided by pi, which is 1. So the period is 1 radian. The phase shift is also 1. It's the opposite of what we see inside of our factored angle. And then the vertical shift is 2. So let's go ahead and sketch our graph. So our phase shift is 1. So that means we're going to go 1 to the right. And I'll just call this right here 1. And what we have to do with a tangent is a little different than what we do with the other graphs. We need to take the period for tangent and we need to center it on the phase shift. With the graph of sine and cosine, the phase shift was the left endpoint of the first period. But for tangent, it's a little different. For tangent, it's the period that has to be centered on the phase shift. So the phase shift is the center of the first period, not the left endpoint. For all the other 5 trig functions, the phase shift is the left endpoint. But for tangent, it is the center. So now we have to go to the left and to the right to form this period of 1. So we're going to go to the left half a unit and to the right half a unit. So now we have an interval here of length 1. Let's apply our vertical shift. Our vertical shift is 2, and that's going to create our so-called center line right there. So we always start with the phase shift, and then we look at the period, and then we go to the vertical shift. All right, there is no amplitude here, so we don't really have to consider the amplitude. Our next step with a tangent that's different than the other graphs is that we need to put in our vertical asymptotes. So the vertical asymptotes for a tangent are at either end of the first period. So we have vertical asymptotes at 1/2 and 3/2. Now we're going to go to our shape. Here's the shape of our tangent. And the shape has just one key point that I really focus on. That one key point is right on the center line, right in the middle there. And it's true that the coefficient out here, it does affect the steepness of the graph. And because there is a 4 that's bigger than 1, this graph should be steeper than a basic tangent. We usually don't plot points, though. We usually just interpret this pretty casually. So we're going to go steep and up if there was no reflection, but lo and behold, there is a reflection. So instead, we're going to go steep and down to the right. And we're going to come in this way from the left. So that's a reflection. We've taken into consideration the last property up here, the reflection in conjunction with the shape to get the tangent function's graph, our transformation. Now let's go ahead and look at the domain and range. The domain for this function, the set of x's for which the function is defined. Well, It's not all reals, but we do say it's all reals except that x is not allowed to be equal to certain values. And the certain values, let's see, how do we figure those out? Well, what we need to do is take a look at the asymptotes. So x cannot be an asymptote. So we figure out the first asymptote, which is 1/2. And then we have to figure out how far apart consecutive asymptotes are. And for the tangent function, consecutive asymptotes are exactly the period apart. So that distance right there is 1 unit. That's how far apart our asymptotes are, 1 unit. So we're going to do 1/2 plus 1 times n. So I don't really need to put the 1 in there. So we'll do 1/2 plus n, where n is an integer. So n is an integer. So that means that as n ranges through all the integer values, we will get all these asymptotes. Let's check. When n is 0, we're at 1/2. Okay, there's an asymptote. When n is 1, we're at 1 plus 1/2. Oh, that's 3/2, another asymptote. When n is 2, we'll be at 2.5. There will be another asymptote. If n was -1, we would be at -1/2, which would be where there is another asymptote. So this is the way we describe the set of asymptotes, and the domain will be all reals except those asymptotes. Now let's go to the range. Range for a tangent function is really easy. The range is all reals, which you could also write with interval notation if you prefer, -∞ to infinity. And the range is all reals because there's no y value that the function does not have. Right? All y values are used by this function. Good luck.